When you look at the world around you, have you ever thought of it as a language? Not one you speak, but one that everything is written in. A molecular language. See, everything you can touch, see, or even feel is built from these tiny molecular sentences. And today, we're going to start decoding it.
So, let's jump right in with a little puzzle. What on earth does the light hitting your eye this very second have in common with, say, a vitamin C tablet? Sounds totally unrelated, right? Well, the answer, believe it or not, is found in that shared molecular language.
So first up, meet our first key player, a molecule called 11-cis-retinol. Just picture a microscopic switch deep inside your eye. When a single particle of light, a photon, comes in, it physically flips the switch, making the molecule change its shape. And that one tiny, microscopic flip, that's it. That's the very beginning of the entire process of sight. Kind of amazing.
Okay, now let's get a little more personal. Let's talk about what's going on inside our own heads. This guy here is serotonin. You've probably heard of it. It's a neurotransmitter that's absolutely vital for regulating our mood. How it works and interacts in our brain? Well, that's a huge part of the chemistry of how we feel.
And here's one we all know, right? Good old vitamin C, or ascorbic acid if you want to be technical. We all know it's essential, it's an antioxidant, and our bodies use it for just a ton of different things to stay healthy. So there you have it, 3 totally different molecules, each one playing a really important role in our lives.
But these are just drawings, aren't they? They're like architectural blueprints. So the real question, the one that really matters, is how do we get from this static picture on a screen to the actual action of seeing or feeling happy or fighting off a cold? How do these molecules actually do anything?
Well, to answer that, we have to learn the grammar of their language. And this is where we dive into the world of what's called organic chemistry. So what even is organic chemistry? Well, the source material gives us a perfect, simple definition. It's just the chemistry of carbon compounds. It's the chemistry of life. This is the field dedicated to decoding that molecular language we were talking about.
And in this language, just like any other, you got to start with the alphabet. For organic chemistry, the most important letter, hands down, is carbon. It is the backbone of pretty much everything that matters.
Carbon has this really cool, unique ability to link up with itself over and over, forming these long chains and super stable rings. The best way to think about it is like a molecular scaffold or maybe a set of Lego bricks. It builds the basic structure that everything else gets attached to. And what's so amazing is how this one principle just scales up. You can start with these really simple carbon chains, but by adding on different atoms and groups, you can build up to these incredibly complex and vital molecules, like the amino acids that make up all the proteins in your body. It's the same fundamental idea, just bigger.
Okay, so we've got our alphabet, carbon, and we've got our nouns, the molecules themselves. But a language is pretty useless without verbs, right? Without action? Well, in chemistry, all that action, everything that happens, it's shown by one simple, incredibly elegant symbol. This is the curly arrow. Now, it might not look like much, but trust me, this little guy is the key to everything. What it does is show the movement of a pair of electrons. And since every single chemical reaction is really just electrons moving around, this arrow shows us exactly how stuff happens.
And hey, don't just take my word for it. Our source material puts it perfectly. It says, this simple device is the one most powerful tool chemists have for explaining how reactions work. That's not just saying it's important. It's saying it's the most powerful tool. It takes us from a boring before and after picture to a dynamic story of how things actually change.
Okay, theory's great, but let's put this powerful tool to work. We're actually going to decode a simple reaction and see how you can read the story that the curly arrow is telling us.
All right, so look at this reaction here. Don't even worry about the fancy names for now. Seriously, just follow the arrow. That's all you need to do. It's telling you a story. It's showing you that an old connection is breaking and a new one is being made. It's our visual guide to the action.
And the grammar for this is so simple. The tail of the arrow, that's where the electrons are starting from. The head of the arrow, that's where they're going to. From here to there. That's it. That is the entire rule.
And once you get that one simple rule, this whole world just cracks wide open. Suddenly we can go from just looking at molecules to actually understanding how they're built, how they interact, and even how we can create totally new ones from scratch.
So why does this one little symbol matter so much? Because by following those arrows, we can finally explain exactly how that retinal molecule in your eye changes shape to let you see.
We can trace the path of a medicine as it interacts with your body. We can decode life itself. And what's maybe most exciting, we can start writing our own molecular stories by designing brand new molecules that have never existed before.
So here's the bottom line. That curly arrow isn't just some doodle that chemists use. It is a powerful tool. It's like a microscope for understanding how the world works, and at the same time, it's a blueprint for building the world we want to create.
It's really the ultimate creative tool, isn't it? It turns chemistry from a subject you just have to memorize into a language you can actually speak. So I'll just leave you with this thought. Now that you know the most important verb in this incredible molecular language, what story are you going to write?